Hi, my name is Keith Colella, and I'm here to present the findings from my thesis for CUNY's Masters of Science in Data Science program. The thesis is titled Assessing Intersection Safety in New York City Using Computer Vision. The focus of this study is on collisions specifically for pedestrians and cyclists in New York City. So we see here on this first slide an overhead aerial image of New York City. This is queried from the Google Maps static API. And it shows all 5 boroughs. If we think about the frequency of collisions, since 2020, there have been over 70,000 involving pedestrians and cyclists, and many more involving motor vehicles alone. We can actually plot the locations of these collisions across New York City. And if we think about the distribution, there are certainly some areas where there appear to be more collisions kind of clustered together. But there is kind of a roughly even distribution across many areas in the 5 boroughs. But if we adjust this plot and make the points where there have been more collisions since 2020, as opposed to those locations where there have been very few collisions, some clear concentrations emerge, right? It's clear that the distribution of these collisions are not evenly distributed across intersections across all these areas. The rate of collision is higher for some spots compared to others. And so this brings us to the central research question of the paper, which is to try and identify whether there are certain physical features, are there certain attributes of these intersections that contribute to the higher rates of collision that are found at those places. So to answer this question, as part of the study, I have trained a machine learning model to programmatically examine aerial imagery of intersections across New York City. Specifically, we're looking at over 27,000 distinct intersections, using that computer vision model to identify certain attributes, extract features from those images, and then examining the relationship of those extracted features with the frequency of collisions at those same sites. So to walk through this paper, I've split this presentation into 3 sections. First, we'll talk a bit about the methodology, how exactly this study unfolded. We'll then look at the results of the statistical models that were used to examine the relationships between those features extracted from imagery and the rates of collisions. And then we'll talk about some implications for potential traffic safety interventions and future research. So to start things off with methodology, again, we'll look at this in kind of 2 parts. First, we'll think about the computer vision model that was trained to identify these attributes, and then we'll talk about the statistical procedure that was used to examine the relationship between the extracted attributes and the rates of collision. And so when we talk about certain attributes, what exactly are we talking about? For the study, we focused on a set of specific features. We tried to identify things that were put in place to specifically protect pedestrians and cyclists, as well as certain features that assist with overall traffic flow in general, or just are necessitated out of the traffic volume at certain intersections. So specifically, we're looking at bike lanes, as you can see indicated on this image. We'll look also at crosswalks. We'll look at certain specialized features such as bus lanes, which you can see kind of peeking out from under this overpass in this image. We'll look at certain traffic flow interventions, specifically medians and double yellow lines that indicate two-way traffic. We'll look specifically at overpasses, which may introduce obstructions or certain kind of environmental complexities that may make it more difficult to see things or navigate intersections. And then finally, we'll look at the intersections themselves. So when we talk about computer vision, there are a few kind of very common techniques. What we've used for this study is called instant segmentation. And we won't go into the technical details there, but the key thing to note is that this instant segmentation model provides 2 key outputs that combine techniques from other computer vision models. So the first output are what we call bounding boxes, which are typical with object detection models. And we can see just for the crosswalks and the bike lanes, those highlighted here. And what these do is they help us identify discrete or distinct instances of certain objects of a given class within an image. So again, if we're looking just at crosswalks, we can see bounding boxes identify separate, distinct crosswalks throughout this image. Same for the bike lane signage on the road. The drawback with these bounding boxes is that they are kind of broad in nature. You can see they give us the general area of where these objects lie, but not the exact kind of pixel by pixel detail. For that, we need that second output, which are these segmentation masks, right? And that's typical of what are called semantic segmentation models. And so these give us, as you can see, a very clear kind of binary mask for each object that allows us to say exactly where in the image a certain item is and how much space it takes up. And we can use that to actually generate measurements for specific objects within the image. And so if we combine these bounding boxes and segmentation masks for all the different classes that we mentioned in the previous slide, we see an example of that output here. And we can use these extracted features for our analysis to see which attributes may or may not be associated with higher rates of collision. Now, as I mentioned before, we can use the bounding boxes to come up with counts, right? We can see the number of medians, the number of double yellow lines, the number of crosswalks in an image. But the segmentation masks we can actually use to come up with measurements. So for example, for the intersections, we can use the masks associated with them to estimate a polygon that fits that mask, and then measure the sides of that polygon to come up with a measurement. Same thing for crosswalks. We can come up with the length and width for each of those crosswalks and use that as features in our analysis. So once we've trained this machine learning model and used it to extract features from all 27,000 of these images queried from Google Maps, we want to then try and start to identify relationships, right? So which of these extracted features may be associated with higher rates of collision. And so to do that, we can rely on kind of more typical statistical techniques. So first, we have to think about this target variable, right? The rate of collisions. And we can see here in this plot, the distribution of collision frequencies, right? The number of collisions experienced at different intersections in the scope for this study since 2020. And we can see that most intersections had no collisions at all involving pedestrians or cyclists. Many had just a few, between 1 and 5. And then as we go further along in this plot, we can see kind of a skew in the distribution form, where there are a number of kind of outliers, a number of intersections that have a really high number of collisions since 2020. More than 20 is the final bucket here, but that it stretches into as many as almost 100 in some cases. In addition to the skew, we have to think about what are called exposure effects, right? So some of these collisions may be related to the fact that simply more people use these roads, right? If we have a road in the middle of Manhattan that experiences a lot of traffic, just simply the number of individuals that are using these roads may increase the number of collisions that are experienced there. And that's not part of the study here. We want to try and control that effect and try and isolate the impact of the specific features that we've discussed previously on those collision rates. So to adjust our response variable accordingly, 2 adjustments were implemented. First, for each intersection, instead of counting the raw number of collisions experienced by pedestrians or cyclists at the intersection, we divided that number by the total number of collisions, which includes collisions of all types, even those just involving motor vehicle, as a way to try and account for this exposure effect. Second, to account for the skew that we see in this distribution, we bucketed these collisions into 4 categorical buckets. And we can see that adjusted version here, where we have a bucket for none, given the prevalence of intersections with no collisions at all. And then we evenly split the remaining between low, medium, and high buckets. This accounts for some of those outliers and prevents those outliers from exerting undue influence on the conclusions that we reach. Now that we have these adjusted collision rates, we can use ordinal logistic regression, which is a way to identify linear relationships between our predictor variables and the likelihood of a given intersection falling into one of these buckets. So now that we have our methodology laid out, we can dig into the results. First, we want to look at those features that have had a strong positive effect on the collision rate, right? So what this means is that these features tend to appear at intersections that have higher rates, right? Intersections that fall into the higher collision rate frequency buckets that we established earlier. And so the first 2 are a little bit counterintuitive. First, we see that for cyclists, bike lane signage actually has a strong, statistically significant positive effect on the collision rate. That is, intersections with bike lanes tend to have higher rates of accidents for cyclists. Now, again, this is a little bit counterintuitive because we expect that bike lanes would provide safety, provide protection for cyclists, and it seems that the effect may be the opposite. However, we don't want to conclude here that these bike lanes are causing accidents or actually making intersections more dangerous for cyclists. Instead, this may be actually just an indication of how pronounced that exposure effect is from before. And again, as a reminder, right, when we talk about exposure, we're saying that it seems cyclists tend to ride on roads with bike lanes more than they do not. And though we attempted to control for this to some degree by adjusting our target variable by the total rate of collisions for an intersection, the exposure effect here may be so pronounced that it comes through even when attempted to control for it. Similarly, with pedestrians for crosswalk width, right? The average width of these crosswalks, which is an indication of how much coverage is provided for pedestrians, we see a strong positive effect here. Again, we don't want to conclude from this that these wide crosswalks that provide a lot of coverage and protection for pedestrians, that these actually cause accidents. But I think, again, this is an indication that pedestrians tend to frequent or walk across intersections more frequently where there are crosswalks in place. Also, there may be some degree of reverse causality here where crosswalks were placed at intersections specifically because there is a higher degree of foot traffic there. However, there are some more kind of intuitive or straightforward findings in the positive effects. Specifically, I'm talking about intersection length and area. So what this means basically is that larger intersections or intersections with very long widths to traverse have higher rates of collisions for both cyclists and pedestrians. The reason for this could be numerous, but this could be an indication that wider, larger intersections have larger streets associated with them, which allows for higher speeds, which may then contribute to accidents. There also may be some kind of navigational complexity in just the amount of area that must be crossed in order to get through these intersections that then contributes to the rate of accident. Similarly, we see that intersection complexity is a positive indicator. And here, intersection complexity was an aggregate measure of the count of intersections, right? In some cases, we would see an intersection abutted by another intersection directly next to it, the count of crosswalks, the count of medians, and double yellow lines. These intersections, as you can see in this example here, are more difficult to navigate, and that navigational complexity may serve to make it more difficult to safely get through these intersections without collisions. On the other side, we do have some strong negative effects, and the most significant negative effects that we saw were actually interaction terms, which are a bit more difficult to interpret, but do provide some important context for the effects we saw previously. So for both cyclists and pedestrians, we see that the interaction between complexity, that complexity index that we discussed previously, and the presence of bike lane signs actually has a negative effect. And so what that means is that while individually both of those things, intersection complexity and bike lane signage, were associated with higher levels of collision rates, when we see those things coming together, there is a negative interaction effect, right? That intersections that are both complex and have bike lanes in place have a lower rate of collisions than we would see otherwise. So this provides some indication that maybe because we were able to some degree account for those exposure effects, we see that in the more complex intersections, bike lanes do have some kind of mediating effect on the rate of collisions that we would expect to see otherwise looking at these two variables independently. Similarly with complexity and crosswalk width, right? Whereas crosswalk width itself was a positive indicator for collision rates, we see that at the more complex intersections, these wide crosswalks may actually help mediate the impact or the higher rate of collision that we see at these intersections otherwise. Finally, we do see the crosswalk gap as having a negative effect on collision rates. And this crosswalk gap is a measurement that indicates areas where there's an intersection without crosswalks, as we see in this example. We can see that only the top and bottom sides of this intersection have a crosswalk, whereas the two areas that cross through this main street do not have any. Now, the original hypothesis for this was that this crosswalk gap would be positively associated with higher rates of collision, because the lack of crosswalks may put pedestrians at danger. But again, I think what we see here is this exposure effect coming through, where pedestrians may tend to avoid intersections or crossing intersections where there are no crosswalks, or that the intersections without crosswalks tend to have less foot traffic in general. And therefore, we see that there are, in places with significant crosswalk gaps, we see lower rates of collision. So thinking about these effects, we can then move on to the actual implications. What does this mean for future research, or for how we can try and plan intersections to be more safe in the future? Before we dive into the details, it's important here that this was not a causal analysis. So we have to keep in mind that correlation is not causation. So while the features that we identified clear relationships in that there are intersections with certain attributes that have higher rates of collision, we cannot conclude that those attributes cause those higher or lower collision rates, right? So if, for example, if we think about bike lanes, we cannot conclude that these bike lanes cause higher rates, because this analysis was not set up to do that. This was meant really just to identify coincidence, right? Attributes that are present at intersections with higher rates of collision. Still, we can look at these results and try and better understand these relationships and think about how we might set up future studies to further that understanding. So the first key takeaway to highlight is related to the exposure effects that we talked about previously. Despite the attempt to control for that effect, it seems that this exposure element still showed through, which really just highlights how pronounced they are. What that means is that, again, roads where there are bike lanes tend to attract more cyclists. Cyclists tend to prefer roads where there are bike lanes. Similarly, with pedestrians, it seems that intersections with better crosswalk coverage tend to have higher foot traffic, and pedestrians tend to use those roads. Now, this may indicate that city planners may be able to actually influence where these pedestrians and cyclists go. Next, we do see a clear effect from size and complexity, right? Intersections with greater size, with more complex navigational aspects, tend to have higher collision rates. This effect is mediated to some degree by certain interventions like bike lanes, but still overall this effect is quite strong. And so from these two things, we may find that city planners may be able to actually improve traffic outcomes by strategically placing key infrastructure. Specifically, they could try and place bike lanes or crosswalks away from the largest, most complex intersections to try and drive pedestrians and cyclists away from those sites. However, as mentioned before, these kinds of conclusions would certainly require additional study. And so we can think a little bit about how this study and others may be enhanced to try and better support or better understand those outcomes. The first enhancement would be to try and better control for exposure. So overall traffic volume provided a reasonable proxy for cyclist and pedestrian volumes, but clearly it wasn't a perfect fit given how much those exposure effects still showed through in the results. Finding specific measures for pedestrian and cyclist volume at a granular intersection level would allow us to adjust our target variable and better control for that effect. Doing that and then seeing which of these effects still persist could allow us to better understand the real relationships between these features and collision rates. Second, we could aim to enhance the computer vision model that was used to extract those features. Specifically, two things could be done. There could be an attempt to train that model to identify other features. We could think about signage or traffic lights and other things that are meant to mediate traffic flow, and add that to our analysis and see which of those features are important in predicting traffic collision rates. And second, we could try and adjust the model to account for other locations, could account for other cities, as well as rural and non-urban environments, and see which of these effects persist across different geographic areas. Finally, we could try and adjust the study to better account for causal effects, or better reflect causal effects. There could be a few ways to do this, but one could involve kind of a temporal analysis where We could analyze the rate of collision at an intersection before a certain intervention was applied, like a bike lane or a crosswalk, and then measure the difference in collision rates after that intervention was applied. This could allow us to maybe better understand how these interventions actually directly cause higher or lower rates of collisions. With that, I will conclude this study. I've left my contact information and the code repository where the study was implemented for those who want to dig further into the details. Thanks very much for your time.